I will begin with a word of prayer. Dear Father, we thank you for today. Again, Lord, I just thank you for these students and this opportunity we have just to be together and study this math. And I just pray you'd help us to understand it more deeply, Lord. In your name I pray. Amen. Okay. So let me just recap what I did last time. So basically the idea, right, is to look at an A-ODE. And it has the form, d to the n plus an minus 1, d to the n minus 1, a2d squared plus a1d plus a naught. So that, acting on, let's say, eta equals to 0, defines a nth order A-ODE. Now, if we call this polynomial, say P, you could say P of D, where P of D is, by the way, an element of the ring of polynomials with coefficients from A in the differentiation operator D. In other words, that's just kind of a unnecessarily sophisticated way of saying it's a constant coefficient differential equation. So, great. Now, I then introduced the notion that we could study this with, basically use the map zeta maps to alpha zeta. And so here maps to exponential of alpha zeta, where alpha is an element of, I think I called it A prime, or you could call it A, I'll use tilde today, just to be weird. So this alpha is a element of an extension algebra to A, all right? And so here, this A tilde specifically, what we're going to do basically is just look at polynomials. I'll use Nathan's notation. So, polynomials in K mod the ideal generated by P of K. So that gives you a extension algebra of A, which has dimension n over A. And you can write this basically as things of the form, say, B naught plus B1K plus Bn. Well, let me make that B1, B2, Bn, K to the n minus 1, such that B0, good grief, B1, B2, B, and R in A, right? Now, we spent a lot of time in Math 422 thinking about this in the case that P is irreducible and that A is a field, right? Then this gives us a new extension field by the maximality of that ideal. But here we have no such luck, right? This doesn't have to be anything nice like that. I'm not assuming that P of K is irreducible or anything like that. So this can have zero divisors. It doesn't have to be anything particularly nice, but we do know that this much is true, that it has dimension n over A, like this. And what that means is that this map up here, which I'm describing, right, if we were to define, let's call this one, I don't know, F and G, so we're looking at what? F, which one comes? Oh, sadness. Tell you what, let me make my life easier and make that a Z. Sometimes you just have to admit defeat. Let's see here. Which I should take the composite of what and what to get that. I think we should look at F. Yeah, F composed with G of Z, right? And I proved that there's a chain rule in this kind of context. And the chain rule is df, you could say df dz tilde perhaps, of g of z times dg dz. So there's a chain rule of a function. I mean, so the you know, g here is a mapping from a to the extension of a, right? And f is a mapping from the extension of a to the extension of a again. So as long as I have a way to multiply a elements in the extension, in other words, if a tilde really is an extension of a, which means that there's a copy of a sitting in there and I can multiply anything in the extension by algebra elements, if I have that much, then it's meaningful to talk about a differentiability in the component-wise sense. All right. Okay, so anyway, there's that chain rule, and then for this one, that just looks like e to the alpha z, right, times d dz of alpha z, which of course is alpha e to the alpha z. Let's see here. So, and then shortly thereafter, we can calculate p if it acts on, you know, e to the alpha z, right? I mean, this is d of e to the alpha z, right? So if we do p, then it generates p alpha e to the alpha z is what happens. To summarize the calculation, when we plug it in to the differentiation operator, each derivative pulls down an alpha in the same pattern as the polynomial p of d, and we got a common e to the alpha z everywhere. We can factor it out. That gives us p to the alpha e to the alpha z, but p to the alpha is what in a tilde? I mean, I buried the lead here, right? P of, well, I'm sorry, P of k equal to 0. So if I'm using k here, I'm sorry, if I'm using k here, what should I be doing down here? It shouldn't be alpha, it should be what? Well, there's different ways I could fix this. I can either change these to alphas, or I can change these to k's. I need to do one or the other. What's your preference? Keep the k's? All right. Keeping the k's it is. K, 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 K. It's very relaxing, really. K, let's see here. All right. No more than 2 k's appearing in a row anywhere, fortunately. Let's see here. And so that is 0 on, I mean, this is in a tilde that is happening, and that is equal to 0 by construction of the extension, right? So I call this A tilde the characteristic extension algebra for the A-ODE. It is the place where this 0 for the polynomial exists. The 0 is k, right? By construction, there is a 0 for the polynomial. And that 0 I can use to construct a solution. Now, this is not a solution to the original problem, right? The original problem, we're looking for eta. What's the solution to the original problem? Should be something like eta is a mapping from A to A, or perhaps an open subset of A to A. Right? That's the kind of solution we're looking for. But what I just found, something a little bit different, right? My solution, quote unquote, isn't that kind of thing. It's a solution. It goes from A to A tilde, right? But the thing is that this e to the k kz, right? If I call that thing g, well, it's really, you know, g. I mean, let me call it h, since g had a different meaning here, right? That's really h1 plus h2k hn k to the n minus 1, right? And so the h1, h2, dot, 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 hn, these are mappings from A to A. These are the component functions, right? Component functions of the e to the kz with respect to the natural monomial basis of the characteristic extension algebra, all right? And I define these to be the special functions of the exponential. You could say that these are the special functions of the characteristic extension algebra. I mean, I think that would be, that may contradict my other definition of special functions in a different paper, but definitely they're the special functions. The component h1 through hn are the special functions of the exponential. That much I think I can say without ambiguity. And so the beautiful thing, of course, is that this, right, this equation p of e to the kz, right, equals to 0. This is a, right, this is a vector equation, right? And basically this filters into n different equations. You know, it's p of h1 plus p of h2 k plus p of h3 k squared plus p of hn k to the n minus 1 equal to 0, right? Because this is a linear differential equation, right? I mean, technically, if you want to get picky, I'm extending the polynomial differentiation operator to the extension algebra in the natural way. It's, in linear algebra, I talk about the complexification of a linear transformation where we basically force the complex unit to be constant with respect to the transformation. In the same sense, we can complexify, if you will, the polynomial differentiation operator by essentially forcing 1 through k to the n minus 1 to behave as constants with respect to the differentiation. So we can pull them out. And in so doing, we find that the solution of h is equal to 0 if and only if every component function of h is separately 0, which is to say that every component function of h is a solution to the original A-ODE. And more than that, so how about the linear independence then? All right, so this basically proves the theorem that, you know, h1, h2, dot, 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 hn as above forms solution set to the polynomial differentiation operator acting on eta equal to 0, right? It forms a solution set. The existence and uniqueness theorem that I sketched the proof of for you guys suggests that if that is a linearly independent set, then we can build any solution with these, so we found the general solution. So it remains to check linear independence of the solution set. How do you do that? Wronskian, huh? Well, I don't quite remember my argument, but like, just let's look at what we got here. The exponential is the thing, right? So we have e to the kz, right? How to say this? I mean, this is an element of the units of the extension, right? So that implies that the matrix with respect to the extension of this thing, right, is invertible. I'm not sure that that's what I need, though. I mean, that's huge. I mean, that's an n by n matrix over A. I'm not sure that's what I need, though. Oh no, I think I forgot my paper. We're on our own today. I have divorced myself from all my previous work. That was dumb. God, so you guys. So I guess we're on our own. How do we prove linear independence of these component functions today? I mean, what I wrote is true. I'm not sure that helps me though. I think you guys are right about the Wronskian though. I mean, if we have, yeah, yeah, exactly. So we have C1. Yeah, that's kind of scary, right? C1H1, C2H2, CNHN. If we set that equal to 0, we'd like to show that those coefficients are all 0. Those are algebra coefficients, of course, taking C1 through Cn from A. I know it's because they're appearing as the components of the exponential function, but it has escaped me why that's enough.
But you said the condition for linear independence of solution is to have the Wronskian invertible, right? Oh,
Zero, if Wronskian equal to 0 implies linear dependence. So as long as it is, invertible.
Right.
Non-zero determinant, they have to be linear.
Well, okay. But the so what's in the Wronskian here? I mean, what does the Wronskian look like? It looks like the first row is the functions, second's the derivatives, and down the line. All right. So how do I use the exponential to connect with that?
I mean, if we're talking exponential, if we talk in exponential, we can pretty much pull the exponential function itself out of the Wronskian matrix, and then we can just look
Whoa.
every time.
No. This exponential is equal to the sum of these functions. There's not a common exponential in here.
Okay.
For example, special example, e to the I theta, cosine theta plus I sine theta. Here's the genesis of this whole idea. So the h1 is cosine, the h2 is sine. I can't pull exponential out of sine and cosine, right?
You take the derivative. I mean, take the of the variables.
I think that's how we do it. Something like that. I mean, I have to somehow do direct combat with this, right? What happens if you take star and you evaluate? I mean, I think we can learn about the values of the function, special functions and their derivatives if we study that equation. To start with, what happens if you plug in z equal to 0? What do we get? Let's see here. Yeah, z equals 0 gives me what? 1 equals to h1 of 0, right? Plus h2 of 0 times k, plus hn of 0 times kn minus 1, yeah? So I learned something. I learned that the functions. So okay, so I think we're getting. You guys are. You're both right. The Wronskian. We need to look at the Wronskian of h1 hn. All right, but we're going to look at it at 0. And the reason that that's relevant is we've proved Abel's theorem. We know Abel's formula for an A-ODE. So we know that the Wronskian, if it's a unit for one value, then it's a unit for all values. Because we proved that we get Abel's formula. So we know that the Wronskian's nice like that. So if we can calculate the Wronskian at 0, we're good to go. And the Wronskian at 0 we can calculate, despite the fact that we don't really want to say specifically what this h's are. For a specific, I mean, I do want to say what they are. I'm very interested in what they are for specific choices of algebra, but not for the purpose of getting through this general argument, right? So we're looking at the determinant of what's h1? So our top row, 1, 0, 0, right? See, because this says more than just h1 of 0, because these form a basis. This implies that h1 of 0 is equal to 0, and hj of 0 is equal to 0 for all j not equal to 1. Because it's a vector equation. Now, what did you say? Somebody said differentiate. So what happens when we differentiate this? We get what? Ke to the kz, yeah, equals to, ay caramba, h1 prime plus h2 prime k plus hn prime k to n minus 1. All right.
Doesn't that kind of give us a little bit of behavior with the h functions though?
I'm sorry?
Doesn't that give us a little bit of behavior about the h functions though, at least like h1?
Oh, yeah, I'm not saying this is useless. I just don't know what it says yet. So if we plug in, again, plug in z equal to 0, what do we get? So equating coefficients, because remember, 1k, k squared, kn minus 1 is a basis in this quotient. Linear independence of a monomial basis, 1k, k squared, kn minus 1, does not use irreducibility or any of that nicer stuff you learned in field theory. Like, the dimension of the quotient is completely based on the dimension of the thing we're quotienting by. The fact that it's an nth order polynomial gives us that this is a basis.
But is there a way we can equate functions? If say we look at the formula k e to the kz, we look at that. Say we divide that second line, the line above where you have green underlines. We divide k by both sides of that equation.
Yeah.
Is there any way that we can possibly equate coefficients or functions to see what they compare to? Like, h1 prime could be possibly like, you know what I'm saying? Like if we divide by k, then we've got like certain things we can eliminate, and then we can maybe equate things
That's
with the regular formula.
That's actually a very interesting question. Can we divide the equation above by k and so discover interesting differential relations between the special functions? To know that would be to know the reciprocal of k in the extension algebra. Whether or not that's possible is the question of whether or not 0 is a 0. Is k equals to, I mean, that's not, the question is k a unit? Is k a unit? You know, when is k going to be a unit? I think k is a unit provided the, I think all we need is that b1 is a unit. Because if b1 is a unit, I can take everything with k to the other side, factor out a k, divide by b1, then I've got 1 is equal to k times stuff. So whatever the stuff is, that's the multiplicative inverse of k in the quotient, yeah. But that's a special thing. I don't have to have that k is invertible. For example, in the extension algebra for the null numbers, if we look at the extension algebra corresponding to y prime prime equal to 0, we'd have epsilon squared. The k squared equal to 0, k would not have an inverse, so we couldn't do that. But I do think you're right. I do think that that's actually an interesting calculation, which would have some, like, maybe not obvious results. But here we can be less adventurous and just plug in 0 into this And then we equate coefficients. Like this tells me that h2 prime of 0 is 1. And it tells me that hj prime of 0 is equal to 0 for j not equal to 2. Which is just a fancy way of me saying that the next row in the Jacobian, the Wronskian, is this guy.
So then if we do an inductive proof, we can probably default that forward by induction. We're just going to get a straight diagonal determinant of the identity matrix, so we know Wronskian is 1. So therefore invertible, so now we know we're going to do that solution.
Right. Yeah. I got to be a little bit careful about how we get what happens at the end of this. Right? When we get, I think it's fairly clear that this will continue, let's say, right up until the last row. Okay? Let's think about that very last step a little bit, right? We would have already, we would have gotten to what? So differentiate how many times? N minus 1 times? Yeah, so what would that do? We would have k to the n minus 1, right? E to the kz equal to like h1, the n minus 1th derivative, plus h2, the n minus 1th derivative at, times k, plus hn, the n minus 1th derivative, times k to the n minus 1. Okay, so it's actually no different. Like the last step is just like the first step. It doesn't even like, sometimes when you do these kinds of arguments in the Wronskian, when you get to the last one, you actually need to go back and use the differential equation itself to do something like a little bit more complicated. But like variation of parameters, if you ever derive the nth order variation of parameters formula, there's an equation waiting for you at the end of that process, which is rather ugly. But yeah, I think you're right, Jess. We just put a 1 there. And so yeah, and since that works out to 1, it follows that the special functions of the exponential are in fact linearly independent and hence form a general solution set, yeah. And that is the solution which was created by Nathan Bedell, which we originally called the stupid solution because it was just too stupidly easy, right? It's just like, yeah. Now, I will take some of the credit. I did the calculus here, but and also the funny thing about Nathan is he hadn't had differential equations before, so it's just very the heavy influence of Math 422 that he had right before we did this. He just got done studying 422 with Sprano, field extension, field extension, field extension. So it's all he's thinking about, field extensions. So when I ask him to solve this problem, what does he do? Tries to build a field extension, basically, right? All right, anyway. So any questions? Should we try to solve a non-trivial one? How about this? What if we were so foolish as to try to solve y prime prime minus 4y prime plus 4y equals to 0 using this idea? Now, first of all, you guys already know how to do it the standard way, right? Lambda squared minus 4 lambda plus 4, which is lambda plus 2 quantity squared, right? So therefore, what's the solution? Oh, t. Okay, fine. Sure, t. Why not? There we go. That's the standard jibber jabber. Okay, so if we're going to do this, let's solve it over an algebra, though, right? So suppose this is a differential equation over an algebra, right? We look at I'm going to take the algebra to be the real numbers just to make things a little bit less weird. And so if we look at the real numbers, well, polynomials in K mod what? K squared minus 4K plus 4, right? Well, this is equal to 1 plus K. Oh, I'm sorry, no. Not just 1 plus k. What is it? What did I do? Do something?
I'm just wondering on the conventional method, like the lambda squared minus 4 lambda plus 4, like how is it the repeated root? Is it a
Yeah,
minus?
it's right. It should be plus 2, not, it should be lambda minus 2.
Oh, did I mean? Oh, I'm sorry.
Okay.
Yeah. I'm sorry. I'm being too flippant. Let's see here. There we go. Yeah. Yeah. So we're looking at things of the form a plus bk, right? Such that k squared minus 4k plus 4 equal to 0, right? But the way I would recommend that you think about this is really what? This is really k minus 2 quantity squared being equal to 0, right? That's like a nicer way to think about it. So we have gone to the trouble, we know that e to the kt, right? That has everything that we want in terms of a solution set. We just need to calculate what does it look like. So given that k minus 2 squared is 0, I want to create a k minus 2. So what I do is add and subtract 2. K minus 2, t plus 2t, right? Then I use the laws of exponents over the extension algebra, as is my right. I have suffered to prove these things. Whether or not people will publish them, that's another story. Let's see here, e to the 2t. So e to the 2t, e to the k minus 2 t, there we go. But that truncates, right? Because k minus 2 squared is 0. So this is just e to the 2t times 1 plus k minus 2 t. Using the power series for the exponential. And then I can collect stuff together, right? What do I got? I've got myself a e to the 2t times 1 minus 2t plus e to the 2t t times k. So that tells me that my solution set is e to the 2t, 1 minus 2t, comma, t e to the 2t, which of course is, a little bit not quite the standard presentation of the solution set, but nevertheless that is equivalent. Because if I can add 2 copies of the second one to get e to the 2t from the first, The span of that pair of solutions is the same as the span of e to the 2t and t e to the 2t, like we traditionally write. But I guess what's neat is not so much that we can solve, I personally, again, it gives me joy that I can solve any real differential equation by a single solution technique. The repeated root case, the distinct root case, they're all solvable by this one method. Like, here's another y prime prime plus 4y prime plus 5y equals to 0, right? So I would look at, a over k over k squared plus 4k plus 5, which is a plus bk with k squared plus 4k plus 5 equal to 0, right? So my solution, z if you will, equals to e to the kt. If I'm using t, it seems to be what we're doing. Well, I guess I shouldn't put z here. I've been using z in a different sense, but what is e to the kt? Well, how should I take advantage of let's see here. So this is what, k plus 2, like that. So you're saying I should split off I should do like e to the minus 2t plus k plus 2 t like that. Like that, right? And then maybe let's let I equal to k plus 2. So I squared equals to minus 1. To make the math a little bit more familiar. See, this is really which then, of course, is 1 plus it minus 1/2 t squared plus 1 over 3 factorial it cubed, that was a minus, plus 1 over 4 factorial t to the 4th, which through the usual song and dance we know, recognize, know, and love as cosine of t plus I times the sine of t. So there you go. E to the minus 2t cosine t plus I e to the minus 2t sine t. There's my y1. There's my y2. y1 comma y2 forms the solution set for this differential equation. That, in fact, is the standard real and imaginary part to the solution that we usually, I mean, that's what the usual complexification procedure produces. Being that this whole idea is a generalization of that, it's not surprising it worked out this way. But at the same time, I think it's cool that we did the same math to solve that one as we did for the repeated root case. You know? What about distinct roots? How's that go? Thank you for helping me not chase this. I mean, I probably should chase that idea further to see where it leads me, but it wasn't helpful today. Well, yeah. Determinant of that matrix actually is the Wronskian. Ah.
It takes more time to expand.
That makes sense because the way, okay, that matrix is obtained by taking e to the kz, and then the next thing is obtained by k e to the kz. The next column is k squared e to the kz, and so forth. We multiply the first column by the basis element to get the corresponding columns in the standard. But see, the trouble is I haven't actually defined that kind of representation. That's a new kind of representation past the one I've been willing to define. That's an algebra. That's a matrix in the algebra representing an extension to the algebra, which is something we should actually write down carefully and write out what you just said, because that's true. Like Daniel Fries at various points has used this without defining it, and then I complain vigorously because we don't know what that means. And then I think he knows in his heart it means something, but he never come back at me with like, well, I'm extending your concept, blah, 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 this is how it's precisely, right? So like, if you did that, I'd be like, cool. But in short of that, fuzzy extensions of ideas I already have, that doesn't work. I mean, we need to be, we have to work within the definitions that we have. Forging ahead into the wild unknown is great, but we also need to be precise. How about this one? So what's a distinct root case? How about this? Y prime prime, here's my favorite one, I don't know, minus 3y prime plus 2y equals to 0. That's a pretty nice one, right? Here you're looking at characteristic values of 1 and 2. So again, we'll look at the, and I'm being a little bit vague, I guess. I mean, technically, I just solved this differential equation over an arbitrary algebra if you think of t as being the algebra variable and not just regular time. It's kind of cool. So Yeah. And I guess technically I'm missing some parentheses here, eh? You know, it's the ideal generated by those characters. All right. So we're looking, you know, A plus BK such that, how's it go? I mean, we could say K minus 1 times K minus 2 equal to 0, right? I don't know if that's particularly helpful, but it's true. Yeah. I mean, how do you use that at the level of the exponential if we... So we know in our heart that e to the kt, and here I'm really thinking of A being the reals for the sake of normalcy, but the calculation just as well extends to the real numbers being replaced with an arbitrary finite dimensional commutative associative algebra. That's neat. What is, how do you make the, how do you do this one? Complete the square. Oh, I think you've got the right idea. You've got the right idea. So instead of looking, so that's a bad path. Oh, I don't like that path either. I don't like this polynomial. Oh, fine, I'll take my medicine. It's a bitter medicine. K minus 3/2. I just hate fractions so much. It's unhealthy. K minus 3/2 squared. And then what do I got? Minus 5/2? Minus 5 what? Minus 1/4? Okay. Well, that's not too bad. So I better add and subtract 3/2. Yeah? So e to the 3/2 t times e to the k minus 3/2 t, right? And let me suggest a notation. Oh, so you're saying, curses. Yeah, I want to make my life easier. Because, yeah, like you said, come on. Well, 2, there's no help. Curses. I'm sorry, I'm having an episode. Let's see here. See, you want to let k minus 3/2 be j, but that's not half of j. J over 2, where j squared is 1, right? I think that's a reasonable notation. Yeah. I mean, you could make it be j, where j squared is 1/4 if you wanted, but let's stick with j meaning j squared is 1 for the sake of, then we'll be able to fall back on things we've already done. So this is what? E to the what? E to the jt over 2? Is that right? And then, by the usual hyperbolic song and dance, that's e to the 3/2 cosh of t over 2 plus j sinh of t over 2. And lo and behold, I get y, 1, and that's the 3/2 t, right? E to the 3/2, 3t over 2, cosh t over 2. That's my first solution. And my second solution, reading the special function off this exponential, e to the 3/2 t sinh of t over 2. Again, I cannot help but emphasize that we have solved the 3 seemingly distinct cases of the second order real ODE by one universal solution method. And of course this, you can repackage. What is this? That's 1/2 e to the what? E to the 2t plus what? 1/2 e to the t. And this guy, 1/2 e to the 2t minus 1/2 e to the t. Yeah. Oh no, it is definitely doesn't seem very efficient. Fair enough. No, I don't. You got me there. You got me there. Yes. Ooh. Okay. But you know, the cool thing is, if we're in H3, right? And we want to solve, like, I don't know, w prime prime plus j squared w equal to 0. We can do it. We just go. So I want e, you know, I want to look at e to the kz, right? Where k squared plus j squared equal to 0. I mean, that's the algebra. And so then, I mean, how do you deal with that? I mean, what does that look like? What's that? Pure series. You don't. You think I did a bad thing? But if
I don't think it has a solution in
well, that's the thing is it doesn't have to have a solution in H3, but it does have a solution. I mean, k squared is minus j squared, right? I mean, oh, I think I know what you're saying. You're saying that I have no choice but to write out e to the kz is equal to 1 plus kz plus 1/2 k squared z squared, right? Right? Fair enough. But the thing is, I can simplify it using that, right? Yeah, there may not be an elementary function, that's true. And I think maybe we should expect that, right? So this, how does this, I mean, what is k cubed? What is k to the 4th? Oh, just j. So we get like that, then minus j squared k over 3 factorial, right? And then what next? J over 4 factorial z to the 4th, right? But the larger point here is that gives us what? 1 minus 1/2 j squared z squared, right? Plus j over 4 factorial z to the 4th plus dot 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 plus k times what? Well, z minus j squared over 3 factorial z cubed. And those are power series representations of the fundamental solution. That's not bad. I never had to drop to the level of real notation to do anything, right? It all happened at the level of algebra notation. That's better. You've done things at the component level. You know what I'm talking about. Yeah. But you're right. I still can't say, oh, look, it's cosine. No, this is the function that need not be named, right? Because you'll only see it here today, right? What application in engineering does this come up in? I don't know.
I feel like it's easy to come up with differential equations with just like that, like
Do that for me.
AC circuits.
Invent for me these AC circuits that use these algebra meaningfully. You have an A in this course immediately. Don't do anything else. If you can do that, like give me an interesting application, game over, your responsibilities here are done, I give you an A.
I was thinking about that from the other day because I
Uh-huh.
was thinking, I said, what if we had like a differential equation that looked like something where we had an algebra component that wasn't real in like the construction of the equation. And I was thinking more about it. I'm like, well, duh. I mean, we get imaginary numbers when we do AC circuits if we represent things as phasors, and I don't see any reason why things would dissipate if we had like certain kinds of circuit constructions that would result in.
Could you use 3 hyperbolic numbers to do like triphase?
I don't think you could use hyperbolics. I think you would still have to use. I think you still have to use imaginary numbers.
Huh.
Yeah, like a three-phase power generator. I think for reasons the fact that it's an AC circuit, you kind of have to stick with imaginary numbers. But I'd have to look at it to be sure. I mean, you could be right. I think it's checking this stuff. Yeah. I just remember there's a three-phase generator. Yeah, those are pretty important for power. What about, okay, random question. So like we're looking over there and we had k squared equals negative j squared. Like why do we never construct algebras in which we have like multiple interesting algebra components? Because like with that right there, like k is equal to ij. Wouldn't that be interesting if we looked at an algebra where I had multiple things like that? I mean, it could be just like an interesting thing. I don't know.
Saying like k is equal to ij.
Yeah.
Um,
Yeah, like you have the same algebra, like this is something we ever discussed. Is there like rules that are being broken that I can't think of?
k is equal to. Hmm. Yeah, I mean, yeah, you could look at the complexification of this problem, and that would be yet another thing we could do. It might make the algebra less ugly.
I was going to say that that'll make it more ugly.
Well, usually adding complex things makes things kind of prettier. But, I don't know. So guys, let's look at our paper, if you don't mind. So, I want to talk about I've had a chance to do some reading in the planar vector field thing. I'm starting to understand it more. And so this is the algebraizability of planar vector fields, that paper, right? Do you guys have this one handy? Ah. No? I have it printed. All right, well, I got stuck when I was reading this because, well, let me get to it. Remember we talked about the autonomous differential equations corresponding to the vector field, which takes it as the integral curve. And then he had this proposition 2.1, which I'll write on the board. And I'm starting to really appreciate, and I think, I don't know, maybe I've got something to add to this. He has after this proposition, he has 3 cases. Well, one thing at a time, I'll do this first. So let f from an open subset of R2 to R2 be Fauché differentiable. All right, then F is algebrizable. Starting to really like that word, algebrizable. Algebrizable. If and only if there exists B1, B2 in 2 by 2 matrices. Hey, let me be civilized. I write that as R2 by 2, right? Linearly independent, such that, and check out this. So the inner product of B sub I with the Jacobian of F at the point x1, x2 is equal to 0, and the trace of your B sub I is equal to 0 for I equals to 1 and 2, and for all x1, x2 in the open domain on which this function is given to be Fauché differentiable. So do you guys know what is the inner product, by the way, of a matrix and another matrix? Do you guys know? The Frobenius norm, right? We take the trace of the matrix times the transpose of it. And that amounts to the Euclidean norm. If you just take the matrix and just run it out as a 4-dimensional vector, it's just the Euclidean dot product of the 4-dimensional vector that corresponds to the 2 by 2 matrix, right? And again, algebrizable means what? It means that we defined that in our previous discussion, but it's essentially captured by the equation that D, where's this stupid thing? Stink. Lost it. I've lost it. Well, the algebrizability was directly in terms of it can it had to do with this d zeta, I think. D squiggle d tau equal to h of thou tau more than that, the and thou squiggle rather of TE equal to F, I think solves, let's say it, F of, basically F of R of T equal to dr dt, I think. I'm sorry, I wrote this out for you guys the other day. I mean, we look at the autonomous system of differential equations like x1 dot equals to f1, x2 dot equals to f2. f1 and f2 are component functions of a vector field. So like the vector field is f1 partial x plus f2 partial x2. So the integral curve to that vector field f1 partial x1, f2 partial x2 is a path such that when we evaluate the vector field at the path, it is like the derivative, right, of the path reproduces the vector field at that. It's, in other words, it's an integral curve. I think this is right. The path, this would be this. So in other words, this is saying that I can set R equals to zeta of TE, and that will solve this.